Hi everyone, this is sixth part in haloalkanes and haloarenes chapter. In our former session we have seen nucleophilic substitution reactions, and I did tell you that in the next session we shall be seeing stereochemical aspects of nucleophilic substitution reactions. Therefore, in this session we shall study about stereochemical aspects of nucleophilic substitution reactions. To understand the stereochemical aspect, you need to have some idea about isomerism that you have studied in your first year. In the first year you have studied 4 types of isomerism. They were generally commonly observed isomerism like chain isomerism, position, functional and metamerism. You might have got some idea about optical isomerism also, which is a type of stereoisomerism. Cis-trans isomerism, you might have studied that, or optical isomerism also. This year you have optical isomerism in detail. So to understand that, let us know first how light behaves. We all know that light travels in the form of a straight line or in the form of a wave. Now ordinary light is composed of waves that moves in all possible directions. It moves in all possible directions or in all possible planes. We can represent that ordinary light as, example, if this is ordinary light which moves in all possible directions, this is ordinary light. If you want this light to move in only one specific direction, what will you do? The common thing that we do is you pass this through a prism that could be of nickel or it could be a polarized lens. So when you pass ordinary light through a nickel prism or through a polarized lens, then the light that comes out of this lens will be able to move in only one direction. Ordinary light which emerges out of nickel prism will move in only one direction. This light which moves in only one direction or in only one plane is called plane polarized light. It is called plane polarized light. How do we get a plane polarized light? When you pass ordinary light through a nickel prism or else through a polarized lens, then the light that emerges out of the lens will travel in only one direction, and we call that light as plane polarized light. So this part is done. Now you understood what plane polarized light is. Now how to identify whether a given compound will be able to pass this plane polarized light or not? So there are some organic compounds like sucrose, oil of turpentine, camphor, etc. All these were tested whether they will be able to pass plane polarized light through them or not. This was done by a scientist called Jean-Baptiste Biot. Biot's observations hold a very great value in optical studies. So this fellow Jean-Baptiste Biot, he passed plane polarized light through the solutions of several organic compounds. I did quote the examples like sucrose, oil of turpentine, camphor, etc. and he found out whether they are optically active or not. How is this done? You take solution of any organic compound, and pass this plane polarized light through the compound, through the organic compound solution. Now if two observations can be seen, this plane polarized light, when it passes through the organic compound, it might come outside. What might come outside? The plane polarized light might come outside, or else it may not come at all. So whenever plane polarized light passes through the organic compound as such, then we say this organic compound, if it allows plane polarized light to pass through it, then we say this organic compound is optically active. If the light does not come out, if no light comes out, then we say the organic compound is optically inactive. So what are optically active compounds? Optically active compounds are those which allow plane polarized light to pass through them, and optically inactive compounds are those which do not allow plane polarized light to pass through them. Our studies are concerned only with optically active compounds. Optically active compounds are those which allow plane polarized light to pass through them. So now this organic compound allows plane polarized light to come out, therefore it is said to be optically active. The property of any compound, the ability of any compound to allow plane polarized light to pass through it is called its optical activity. Optical activity is defined as the property of any organic compound to allow plane polarized light to pass through it. It is called optical activity. Now the next part is dextro and levo compounds. Now we know that our organic compound is optically active. How did we try this? By passing plane polarized light. Now the light that comes out through this compound, plane polarized light which comes out through this compound, it can move in two directions. Either it can travel in this direction, or else it can travel in the opposite direction also. There are two possible ways. If the plane polarized light which gets rotated, if the plane polarized light after coming out through the organic compound, if it gets rotated in right hand side, or else if it gets rotated in clockwise direction, then such compounds are called dextro compounds. This rotation is called dextro rotation. Dexter, in Latin, dexter means right. Therefore, if an organic compound rotates the plane polarized light to the right hand side or in clockwise direction, then such organic compounds, such optically active organic compounds are called dextro compounds. If the light that comes out of the organic compound gets rotated in anti-clockwise direction, if it gets rotated in anti-clockwise direction, or else if it gets rotated in left hand side, then we call such compounds as levo rotatory compounds. In Latin, levo refers to left. So light comes out of the organic compound, then we call such organic compounds as optically active. Now light is coming out, this light is getting rotated in clockwise direction, then it is dextro. If the light is getting rotated in anti-clockwise direction, then it is levo. So this was another concept, dextro and levo rotatory compounds. Dextro rotatory compounds are those which rotate the plane polarized light to the right hand side or in clockwise direction. Levo rotatory compounds are those which rotate the plane polarized light in left hand side or in anti-clockwise direction. I hope till here all the concepts are clear. Plane polarized light is the one which moves in only one plane or in only one direction. If that plane polarized light is able to pass through an organic compound, then it is optically active compound. The property of a compound to show optical rotation is called its optical activity. Based on the optical activity, based on the rotation of plane polarized light through the organic compound, organic compounds can be of two types, dextro and levo. If the plane polarized light after coming out through the organic compound gets rotated in clockwise direction, then it is dextro compound. If it gets rotated in left hand side or in anti-clockwise direction, then it is levo rotatory compound. Then what is optical isomerism? Optical isomerism is defined as a phenomena in which two compounds, normally two compounds or else more compounds, therefore two or more compounds which have same structural formula, same molecular formula. But how do they differ? They differ only in the mode of rotation of plane polarized light. Two or more compounds having same molecular formula and structural formula but differ in the mode of rotation of plane polarized light are said to be optical isomers, and the phenomena is called optical isomerism. So there are two compounds, one is dextro compound, the other is levo compound. So these two are isomers. What kind of isomers are there? They are optical isomers because they differ in the rotation of plane polarized light. One rotates to the clockwise direction, the other to the anti-clockwise direction. So it is optical isomerism. Optical isomerism means two or more compounds having same molecular formula and structural formula but differ in the mode of rotation of plane polarized light. One rotates in clockwise direction, the other should rotate in anti-clockwise direction. Such isomers are called optical isomers, and the phenomena is called optical isomerism. For a compound to show optical isomerism, we have some criteria that forms our next topic, criteria for optical isomerism. These criteria are important for all competitive exams, for theory exams, as well as all of your upcoming exams like NEET, JEE, AIEEE, etc. Criteria for optical isomerism. For a compound to show optical isomerism, you have two conditions. One, no plane of symmetry. The second is presence of chiral carbon. This means for a compound to show optical activity, for a compound to be optically active, for a compound to show optical isomerism, for a compound to show either dextro or levo rotation, it should satisfy these two main conditions. One condition is no plane of symmetry. Let us understand what is plane of symmetry. Take example of methane. In methane, if I write methane in this form, and if I ask you to divide this molecule into half, how will you do this? You might pass a plane through the exact center of the molecule. For example, if this is the plane, okay. Now if one part of the molecule looks similar to the other part of the molecule, then we say plane of symmetry exists. If this part of the molecule does not resemble the other half, then we say plane of symmetry is absent. So what is plane of symmetry? Plane of symmetry is an imaginary plane. It does not exist, but we have to imagine. It is an imaginary plane which when passed through a molecule should cut the molecule, should divide the molecule into two equal halves, so that one half of the molecule becomes the mirror image of the other half. Understood? It is an imaginary plane which when passed through any molecule should divide the molecule, should cut the molecule into two equal halves, so that one half of the molecule becomes the mirror image of the other half. If this happens, if plane of symmetry is present in any molecule, then we say such compounds are optically inactive. So molecules which contain plane of symmetry are optically inactive. For a compound to be optically active, plane of symmetry should be absent. It should not exist. Then the second condition is presence of chiral carbon. Chiral carbon goes by different names. Chiral carbon is also called as asymmetric carbon. It is also called asymmetric carbon. What is asymmetric carbon? It is a carbon which is attached to four different groups. Say methyl group, one fluorine, one hydroxyl group, one chlorine. This is just an example. So if any carbon is attached with four different groups, then we say this carbon is a chiral carbon. It is a chiral carbon. A chiral carbon is otherwise called asymmetric carbon. If in any molecule there is an asymmetric carbon atom, there is a carbon atom to which four different groups are attached, then such molecules will be optically active. An asymmetric carbon atom is indicated by writing an asterisk over that carbon. Understood? For a compound to be optically active, it should contain at least one. It should contain at least one asymmetric carbon atom. It should not contain plane of symmetry. Many a times you will be able to getting confused. Sometimes in the molecule you will be able to see plane of symmetry exists. I will show you one example. See, CH3, CH2, CH, Cl, then CH3. Now, how to identify whether a compound is containing a symmetric carbon atom or not? Let us see that first. So, you write this molecule into split form. This is in condensed form, you write its structural form. There are 4 carbons, 1, 2, 3, 4. Each carbon has got hydrogens. So, I will write as it is, CH3, CH2, here CH3, here H, here Cl. So, this carbon, you see the first carbon has got 3 hydrogens, 1, 2, 3. The second carbon has 2 hydrogens, the last carbon has 3 hydrogens. Beginning from the first carbon, in this carbon, it is attached with 3 same atoms. Can it be asymmetric? No, it cannot be asymmetric. Look at second carbon. One side it is attached with methyl group. The entire group is to be treated as one. It is not to be counted as carbon. So many of you will confuse, here is one carbon, here is one carbon, 2 atoms are same. No, this entire is one group. Then this is one group. 2 are different groups, but there are 2 same hydrogen atoms. So this cannot be a symmetric carbon atom. Now look at third carbon. On one side it has ethyl group. On one side it has ethyl group, CH3, CH2, one group, okay. The other side it has methyl group, 2 different groups. One side it has hydrogen, third different atom. The fourth side it has chlorine. Therefore, this is a symmetric carbon atom, okay. Then 4th carbon, 3 sides same hydrogens, one side different group. So, it cannot be a symmetric carbon atom. So, in this example, out of 4 carbons, we have 1 carbon which has different groups attached to it. Therefore, it is an asymmetric carbon atom. Molecules which contain asymmetric carbon atom or chiral carbon atom, which contain chiral carbon atom, they are optically active. They will show optical isomerism. Molecules which contain chiral carbon atom or asymmetric carbon atom, they are optically active. They will show optical isomerism. Do they contain plane of symmetry? No. If you are saying, if you are observing any asymmetric carbon atom, it will never have plane of symmetry. You cannot cut this molecule into exact half and see that its 2 mirror images are same. Its mirror images will never be same. Molecules which contain asymmetric carbon atom will not contain plane of symmetry. What does it contain? It contains only chiral carbon atom. Whether it shows optical isomerism? Yes. Whether it will show optical activity? Yes. Whether plane polarized light will come outside? Yes, it will come outside. Does it contain plane of symmetry? No, it does not contain plane of symmetry. So, what are the criteria for optical isomerism or optical activity? It should not contain plane of symmetry and it should contain chiral carbon or asymmetric carbon atom. If it contains asymmetric carbon atom, it will not contain plane of symmetry. If it is containing plane of symmetry, it is likely that it will not at all have any chiral carbon atom. Molecules which do not contain chiral carbon atom, such molecules are called achiral molecules. They are called achiral molecules. Now tell whether this molecule is chiral molecule or achiral. This is chiral because it contains asymmetric carbon atom. You tell whether this molecule, it is also chiral molecule. And then this example, it is, sorry, I will give you one more. Okay. Now if I ask you this to cut this molecule, you will cut here. This part and this part both look same. So plane of symmetry is existing. Whether it will show optical activity? No, it will not show any optical activity. Whether it will show optical isomerism? No. Is there any chiral carbon atom? No. Is there a symmetric carbon atom? No. Is there plane of symmetry? Yes. Will it be optically active? No. Then what will it be? It will be optically inactive compound. I hope this part is clear. Then we shall go on to chirality and chiral molecules, that I have already told you. What is chiral molecule? A chiral molecule is the one which contains at least one asymmetric carbon atom. Molecules which contain at least one asymmetric carbon atom will be chiral molecules. And the property to show optical isomerism, such compounds are called chiral compounds, and the property is called chirality. Then we have enantiomers and diastereomers. This part is important. Now let us consider this example. CH3, CHCl, CHBr, CH3. Notice in this example, are there any asymmetric carbon atoms? If you are not able to identify in this condensed form, you can write it in their structural forms. I will write their structural forms. There are 4 carbons. The first carbon with 3 hydrogens, second with hydrogen and chlorine, third with hydrogen and bromine, last with again hydrogens. So in this, keep on observing from the top. The first carbon has 3 same groups, no asymmetric. Second carbon, 1 hydrogen, 1 chlorine, 1 methyl, 1 different group. So this is asymmetric. Third carbon, 1 hydrogen, 1 bromine, 1 methyl, 1 different group. So this is also asymmetric. Fourth, non-symmetric. So there are 2 asymmetric carbon atoms in this example. So this compound will obviously show, optical isomerism. If I ask you to write its mirror image, how will you do? You first draw an imaginary line, assume it as mirror. Let us say this is mirror. Okay. Its mirror image will look like, see 4 carbons as it is, 4 hydrogens, many hydrogens, here Cl, here H, this side Br and this side H. Again the middle 2 carbons are asymmetric. Okay. These 2 look similar, aren't they? Both are mirror images. Both look similar. Let us say this is first isomer, this is second isomer. Is there any other possibility of writing the skeletal arrangement of the compound? Yes, we shall see the next one. Again 4 carbons as it is. This time I will write Cl here, H here, and Br as it is in its place. Its mirror image will look like, how will its mirror image look? Again 4 carbons, last carbon 3 hydrogens, first carbon 3 hydrogens, middle carbon, this side hydrogen, this side chlorine, this side hydrogen, this side bromine. The middle 2 carbons, second and third carbons are asymmetric. Let us say this is third isomer, this is fourth isomer. Simply looking at asymmetric carbon atoms, you can tell how many number of isomers it can be formed. So there are 2 isomers, there are 2 asymmetric carbon atoms. So 2n formula is followed, where n is the number of asymmetric carbon atoms. So 2 to the power 2 is 4 isomers are possible for this compound. These are 4 isomers. Now in these 4 isomers, isomer 1 and 2, these are mirror images. 3 and 4 are mirror images. 1 and 3 is not at all linked, 2 and 4 are not at all linked. Now in the first 2 isomers, 1 and 2, you will say that these 2 are mirror images of each other. Similarly, third and fourth are mirror images of each other. keep the second isomer as it is, lift the first isomer, keep it on the second. Do not tilt. If this is one isomer, this is another isomer, you lift the first isomer, place it on the second without turning the first isomer. You are not supposed to do like this. Understood? Lift the first isomer as it is, keep it on the second. Tell whether these two isomers are coinciding, whether the atoms present in them are coinciding. Do they match? If I lift this molecule and keep it on or place it on the second one, this Br will come here. So they are not getting imposed. So they are called non-superimposable. They are called non-superimposable mirror images. They are mirror images. Are they able to overlap each other? No. They are non-superimposable. So, are they optically active? Yes. So, the optically active compounds which are non-superimposable mirror images, they are called enantiomers. What are enantiomers? Enantiomers are optically active because they contain asymmetric carbon atom. They are optically active. They rotate plane polarized light. They are optically active isomers which are non-superimposable mirror images of each other. Understood? Now, third and fourth, are they mirror images? Yes, they are mirror images. Are they superimposable? Means lift the third image, keep it on the fourth one. Do they coincide? No, they do not coincide. Therefore, do they superimpose? They do not superimpose. Therefore, 3 and 4 are also non-superimposable mirror images. Therefore, isomers 1 and 2, 3 and 4, they are non-superimposable mirror images. Therefore, they are called enantiomers. Now, time being, assume that second does not exist. You lift the first one, place it on third one. Are they imposable? No. Are they mirror images? No. But are they isomers of same compound? Yes. Then isomers 1 and 3, similarly 1 and 4, similarly 2 and 3, 2 and 4, they are not mirror images. They are not superimposable. They are simply isomers of the same compound. They are simply isomers of the same compound, and such isomers are called diastereomers. Diastereomers are the isomers of the same compound, but they are not mirror images. They are not superimposable. Understood? Diastereomers are 1 and 3, 1 and 4, 2 and 3, 2 and 4. They are not mirror images. They are not superimposable, but they are isomers of the same compound. What are enantiomers? Enantiomers are mirror images. They are optically active. Whether diastereomers are optically active? Yes, they are also optically active. Enantiomers are optically active mirror images but non-superimposable. Diastereomers are optically active isomers of the same compound. They are not mirror images. They are not superimposable. If these parts are over, the next part is racemic modification or racemic mixture. If any compound has got these two enantiomers in equal proportions, say if this compound is able to rotate light in clockwise direction and the other compound was rotating in anti-clockwise direction, if these two exist in 50-50 ratio, then we say such a mixture as racemic mixture. An enantiomer has 100% optical activity. Two different enantiomers will have different optical activity. If this rotates light in clockwise direction, the other isomer will rotate light in anti-clockwise direction. Their optical rotation, their specific rotation will be different. If these two exist in a molecule in equal proportions, means 50% of the molecules are in D forms, 50% of the molecules are in L forms. If this happens, then such a mixture compound is called racemic mixture or racemic modification. What do you think, the molecule will have optical activity or not? I mean, An enantiomer is optically active, diastereomer is optically active. What happens to the activity of racemic mixture? A racemic mixture will be optically inactive because it contains two isomers in equal proportions. So if 50% of the molecules are rotating in clockwise direction, 50% of the molecules are rotating in anti-clockwise direction, then their net optical rotation gets cancelled. As a result, racemic mixture will have zero optical rotation. It will have zero optical rotation. Even though asymmetric carbon atoms are present, its optical activity is zero. Therefore they are optically inactive. They become optically inactive because of the presence of two enantiomers in equal proportions. Understood racemic mixture or racemic modification? Now we have come to the last part, retention and inversion. Let us see how this happens. In any chemical reaction, say we have a reaction of this type, a molecule with carbon and different compounds, different atoms or groups attached to it, A, B, C and say X. We are more concerned about this bond, no? Carbon and halogen bond. So in this compound, if you want this halogen to be replaced by some other nucleophile, let us subject it to a nucleophilic substitution reaction wherein you are bringing a new group, that is Y. You are adding a new nucleophile, you are substituting a new nucleophile in this compound. Then what should go? X should go. X should go away, giving place for Y. Then what will be the product obtained? C as it is, A, B, C. In its place who comes? Y. This is one set of reaction. This cannot be the arrangement. Sometimes the reaction may takes place in a different way. Again assume that you are substituting X by Y. When Y approaches, X goes away, X leaves. Then the product will be here A, here C, here B. What should come? Y. But Y will take place here. How are these two reactions different? Once X is substituted by Y, and if Y takes the same place as that of X, we call that condition as retention in configuration. If in the product the incoming nucleophile has taken place opposite to that of the existing nucleophile, then we say it is inversion in configuration. The third possibility is that, now let us say this is product A and this is product B. In the third case, if you are removing X and if you are substituting it by Y, and if you get both the products A and B in the ratio 50-50, then we call this as a racemic mixture. So what is retention? If the product formed has same configuration of groups, as that of the reactant, then it is retention in configuration. If the product formed has opposite relative configuration as that of the reactant, then it is inversion. If both the reactions take place simultaneously to give products in 50-50 ratio, one having retention, the other having inversion in equal proportions, then it is racemic mixture. We see retention in which nucleophilic substitution reaction? We see this in SN1. Inversion is seen in SN2. Racemic mixture is not so common. So today we have studied all the stereochemical aspects of nucleophilic substitution reactions. To understand what retention and inversion is, we had to study all these parts. So in the next coming session, we shall see some other part of this chapter, that is haloarenes. Thank you.